Sooner or later, the shine wears off any relationship. Perhaps, accidentally, you'll leave them out in the rain. And before you know it, unsightly rust. Fortunately, our exploration of electrochemistry has explained that rust works like tiny batteries all over the robot's iron skin. Each drop of water which falls on the robot acts like an electrochemical cell, with an anode and a cathode, a pathway for electrons to flow, and a salt bridge. That's the droplet itself, where migrating ions form unsightly iron oxides. If electrochemistry is the problem, it's also the solution. We can galvanize our robot by dipping him in a bath of zinc, which loses electrons more easily than iron. It's the zinc that oxidizes to leave a protective coating of zinc oxide. Safe, but very dull. A little flashier protection comes from robot jewelry, a sacrificial anode of magnesium. This forces the iron under a droplet of water to become a cathode. Magnesium donates the electrons, and the iron passes them on to the drop of water without losing electrons itself. Of all the ways of protecting your robot, the flashiest of all turns the robot into an electrode, connected to another electrode in what looks like an electrochemical cell. But there's a big difference. In a battery, we have chemical change, producing electrical energy. A horrible form of cannibalism. But if we change the process by putting a battery in the circuit and reversing the current, electrical energy now produces a chemical change. We can clothe our robot in a gleaming coat of chromium. This process is known as electroplating. We'll explore the process using a more familiar metal. We'll start with water and add copper sulfate. Most of the copper sulfate is in the form of positively charged copper ions and negatively charged sulfate ions. A very small number of water molecules will dissociate to form positively charged hydrogen ions and negatively charged hydroxyl ions. The remaining water molecules, although neutral, have regions which are slightly negative and regions which are slightly positive. That's because oxygen has a stronger attraction for electrons than hydrogen. We'll begin the electroplating process with a pair of carbon rods for electrodes. Of course, nothing happens. By now we know that they have to be connected for a charge to flow. But we won't stop there. We'll insert a battery in the circuit. Now we've got action. Copper atoms begin to plate out on one electrode. At the other electrode, bubbles are forming. What's happening? Let's explore the electrochemistry. The negative terminal of the battery pushes negative charges on one electrode. This electrode repels negatively charged hydroxyl and sulfate ions. It attracts the positively charged copper and hydrogen ions. It also causes water molecules in its vicinity to orient themselves so that the positive parts are nearer the electrode. You might think that positive ions and water molecules could all be reduced by accepting electrons from the electrode. But that's not what happens. It's as if copper ions intimidate the other particles and grab all the electrons for themselves. We can explain this by examining the half-cell reactions involved. Hydrogen ions, in fact, are not in a standard concentration, but scattered throughout the water. And so the reaction has a very low half-cell potential. And so does this reaction, compared to the copper reaction. Consequently, the copper ions grab the electrons and are reduced. As they do so, they plate out on the electrode. This reaction, the reverse of a battery reaction, is called electrolysis. The atoms of metal which plate out on one electrode gives industry its major use for electrolysis, the process known as electroplating. Since reduction is occurring here, the negative electrode acts as a cathode during electrolysis. Now, let's look at the positive electrode, which acts as the anode. The positive charge repels the hydrogen and copper ions, but it attracts the hydroxyl and sulfate ions. Water molecules nearby orient themselves so that the slightly negative oxygen is closest to the electrode. Let's look at the possible reactions and their potentials. Now, these are reduction potentials, but we are considering the oxidation side of the reactions. So we must reverse these reactions and change the signs of the potentials. This reaction has the most negative potential, so it won't occur. The remaining two reactions have the same potential. Let's explore the water reaction. Two water molecules lose electrons to the anode and form a molecule of oxygen gas and 4 hydrogen ions. It's the oxygen molecules that we see bubbling up at the anode. While the hydrogen ions tend to remain in solution, migrating towards the cathode with the other positive ions, the negative ions migrate towards the anode. This migration of ions keeps the overall charge of the solution neutral. By combining the reaction at the anode with the reaction at the cathode, we can determine the overall reaction, as well as the overall potential. It's a negative potential. This means that the reaction won't occur spontaneously. And that brings us to the reason for the battery. We need an electrical potential higher than 0.48 volts to overcome the negative potential of the process. In place of the carbon cathode, put a robot, and we can have a copper-coated robot. Or, with different ingredients, a chrome-plated one. Electrochemistry, the curse of every Iron Man, causes rust. But electrochemistry is also the cure. So, if you're planning life with a robot, take heart. Better still, take a pack of 4. You'll need them to keep alive that special electrochemical romance with a robot.